All right, so today we're going to talk to you about correctly extending dominance to MLIR regions. And take it away, Sid.
Cool, thanks, Jeff. Right, here's the agenda. We're first going to give sort of like a recap on dominance for those of you who might have forgotten. So I'm going to define dominance for you and dominator trees, because that's what the rest of the talk is going to use. We're then going to discuss how it's implemented in LLVM a little bit. And then more importantly, we're going to then move to how dominance works in MLIR and maybe sort of problems associated to it. And we propose solutions. And yeah, so let's go ahead. Right. So let's first begin by talking about dominance in LLVM, right? Like, what is dominance? Why is it useful? What does this concept do? So let's assume we have this control flow graph where we have these 4 basic blocks, and I have a constant 10. This is, there's a variable called %x, and then I have another variable called %z in the SSA IR that uses x. Now the question is this IR legal? And the answer is, well, no, it's not. If you throw it into LLVM, it'll complain, right? And why isn't it legal? Why isn't it legal? Well, the reason it's not legal is because there's this execution path highlighted in pink, through which essentially, we can get to z without ever having defined x. So intuitively, this is why it's illegal. It's because the variable %x is unavailable in the path from the entry to the basic block that reaches %z. So we say that in this situation, the basic block 1, which contains x, does not dominate basic block 3, right? So this is illegal. Now there's a question of, okay, we use it to define legality, but do we ever need it in any real situation? Is it actually useful? Can we just ignore it? So the answer is, dominance is generally used by passes which try to reason about variables and reachability and liveness. So let's take an example of constants of expression elimination. So let's assume we have this variable x, which computes something really expensive. And then we also have z, which again computes something really expensive. So if this is our control flow graph, then we can ask the question, well, can we always sort of replace the value %z with %x? And the answer is yes, we can, because whenever we reach the value %z in basic block 3, we always get to basic block 1. And so it's safe to perform this particular CSE. So now for a non-example, let's change the control flow graph. Let's imagine that we have a control flow graph that looks like this, where we once again have this diamond shape. And if we again ask the question, is it safe to replace? Then the answer is, well, no, it's not, because for the exact same reason as before, it's not legal to actually replace z with x, because x isn't always reachable. And so CSE is illegal. So, okay, now we've gotten a feeling for what dominance is and how it's used in LLVM. I'm now going to do a little bit more of, let's say, a formal definition of this, so that when we get into discussions about MLIR, we'll have a clear understanding of what we're doing. So dominance. So right here, okay, so we say that a basic block P dominates a basic block C, where P stands for parent and C stands for child. So let's just choose 2 basic blocks, like 2 as the parent and 3 as the child, if and only if every path from the entry to the child passes through the parent, right? Now this is kind of annoying to unpack because it contains a quantifier, so let's think about it, what this means. So let's pick one particular path. Okay, we've picked this path. It's a path from the entry to the child, and it does pass through the parent, right? Okay, so far so good. Does this mean that we've checked dominance? No, it's not, because we need to consider all possible paths. So in this particular case, we can see that 2 does dominate 3. And the idea is that we think of all possible paths from the entry to 3. And essentially, all such paths can go from the entry to 2, cycle around a bit on this cycle, and then get to 3. And so therefore, it does in fact dominate. But this was some sort of ad hoc reasoning that we did. Now, for a non-example, we could ask once again, if I choose 4 as the parent and 5 as the child, does 4 dominate 5? And the answer is, as previously, no, it doesn't, because I can choose this path from the entry to 5 that doesn't go through 4. So that's a non-example of dominance. So we can ask the question, okay, how do we actually compute this in practice? Because it seems like we need to consider an infinite number of paths, right? Like the definition says for all possible paths. So you can't just trivially check things. You need to somehow enumerate an infinite number of things. So I'm not going to actually explain how we compute dominance. You're going to have to trust me that LLVM is capable of computing a data structure called as a dominator tree, which represents this piece of information. So next I'm going to explain what a dominator tree is. And yeah, because that's what will be used eventually in MLIR. So what is the dominator tree? Well, the intuition is that the dominator tree captures this information of the basic blocks dominating each other by talking about the closest dominator. So we have the control flow graph on the left. I'm going to show you the associated dominator tree on the right, which captures the dominance information in this control flow graph. So first, I'm going to have the entry block in the dominator tree. OK, that's done. Next, let's consider basic block 2. So the idea is, OK, the entry block does dominate basic block 2. So there's going to be an edge from the entry to basic block 2. Next, if we think about basic block 4, well, we can ask the question, which basic blocks dominate basic block 4? Well, the point is both entry and basic block 2 dominate basic block 4, because every path from the entry to basic block 4 goes through both the entry and 2. But intuitively, 2 is like closer to 4 in the control flow graph. And so therefore, we attach 4 to 2. So if we repeat this process for all the basic blocks, we end up with a tree that looks like this. OK, we have this data structure, which I claimed as a dominator tree. How does this actually help us compute dominance? Well, let's use it. So let's try to use it to compute whether 2 dominates 3. As we saw before, it does. And the idea is that in the dominator tree, you check if 2 is a parent of 3. It is, and so therefore 2 dominates 3. Now, for a non-example, if we want to check if 4 dominates 5, we check if 4 is a parent of 5 in the dominator tree. Well, they aren't, they're siblings, and so therefore 4 doesn't dominate 5. So the information of dominance within LLVM is encoded within this data structure called as a dominator tree. Also, this is like sort of a plug. The actual algorithm is quite beautiful but complicated. There's an interesting talk from a few years ago by Jakub, who implemented the algorithm of dominance tree computation. It's a really cool talk. You should go take a look. Anyway, yeah. So I'm now going to hand it off to Jeff, who's going to describe the story in MLIR.
So MLIR happens to also have control flow graphs, like LLVM. And so the obvious question to ask right away is, are there any differences? Well, not really, besides indirect go-tos, which are super niche, and you shouldn't be using them anyways, unless you happen to be stuck in that kind of situation. And that means that all of the LLVM infrastructure for computing and working dominance can be reused in MLIR. So the MLIR dominance analysis will actually just instantiate the LLVM dominator tree base with an MLIR block. And then we can reuse this super cool algorithm for computing dominance in MLIR too, which is great. It's code reuse. Special mention is actually block arguments. So block arguments are a pretty significant representational difference between LLVM phi nodes and MLIR. And I think that's a very interesting discussion on its own. It was something that's been debated in the community as well. But from the perspective of dominance, it's really just semantically equivalent to phi nodes. It doesn't change anything. MLIR has this cool new thing called regions, and that pun is intended, by the way. The MLIR Lang ref says that a region is an ordered list of MLIR blocks. OK, well, that says not much. But actually, MLIR has 2 different kinds of regions. Originally just 1, but now 2. One is called SSA CFG regions, and another one is a bit weirder, but a bit newer, called graph regions. So an SSA CFG region is like it's what you expect. The region contains a control flow graph, and the operations in that control flow graph obey SSA. And what that basically means is you can't use the result of an operation before that operation has been executed in the block. The other important property is that the first block in a region is always the entry block of the CFG. So CFGs always have an entry block. Graph regions are used in MLIR to represent graphs. They are single block, although this is just a present limitation. And the important thing is that the block in graph regions can be used to represent graphs with MLIR ops. And what that means is that the MLIR op can use results before they're defined. So in this example, we have %C that is used in the definition of %B before it is defined. And in fact, %C is used in its own definition. So we have cycles in the graph, and the region doesn't have to obey topological order. So it turns out that the semantics of regions within them are partially defined by MLIR. But actually, the semantics across regions, in multiple senses of the word, is completely defined by the parent operation. So the Lang ref says that the containing operation defines the semantics of the regions it contains. And this actually is where the problems start to come. Because MLIR ops can mean whatever you want them to mean. And consequently, region semantics could be whatever you want them to be. So let's talk about some of the problems, but before, let's explain what dominance really is. So the region is different because a region defines like nesting of operations within other operations, which is great because a function can just be defined in MLIR as an operation with a region. And that region contains basic blocks, it contains ops. Those ops can then contain other regions. So if you've never seen the generic syntax for MLIR regions, it's just like paren, squiggly bracket, region 1, region 2, and so on. And then we also have implicit captures. So a region can capture SSA values that are defined outside the region and use them inside. This is valid because region in MLIR form a tree called a region tree. And it is said that the parent region always dominates its child regions. So operations in the parent region dominate operations in the child regions if that op comes before the owner of the child region. So I'll pass this over to Sid for a bit to explain some of the details of dominance in MLIR.
And so, well, how is this implemented? So the way in which it's implemented is really straightforward. The algorithm's implementation looks quite ugly. We won't go through it. So I'll explain via picture. So, as Jeff said, we have these regions that are nested. And so for every region in the region tree, we have a control flow graph. So we compute the dominator tree that corresponds to every control flow graph. And then what we do is we add these like virtual edges between the dominator trees of the parent and the dominator tree of the child. Now note that these edges are added regardless of the operation semantics. So there's a tension here because when we talk about dominance, we're actually talking about control flow, right? Like we have edges in a control flow graph based on control flow, but the region tree is based entirely on syntax. And so this leads to this weird tension where the data in each dominator tree is semantic because it talks about control flow, but this edge that's added by MLIR between these dominator trees is purely syntactic. And now I'm going to hand it back to Jeff to show how this can be used to do interesting things.
So we'll start with the sane world. And the sane world basically is just functions and control flow. So you have functions, you have function calls, these are direct calls, and you have control flow, i.e. control flow graphs. So for example, in MLIR, we have structural control flow, which uses single block regions typically, and uses region nesting to define say, ifs, conditionals, loops, switches. And this is great because it's a little bit easier to read, it's easier to reason about, and the kind of syntactic dominance does actually equate to control flow dominance. And you even get stronger guarantees on control flow, like it is guaranteed to be reducible if expressed with regions that have these semantics. So which means that these sort of structured control flow is semantic equivalent to control flow graphs. And so everything applies, everything about dominance that applies to control flow graphs applies to these kinds of regions. So one use of dominance that in MLIR, for example, could be mem to reg. Mem to reg relies on dominance to compute the liveness of local variables. So in this example, we have %var defined by a stack allocation. And this use of %var inside the region is in the child region of the function. And therefore, we say that the variable is live at this load. More importantly, the nearest dominating store of the load is the store of %arg0. And so we can replace the load of var directly with arg0 and promote this variable off the stack. It's very useful. It's a great optimization. Things get a little bit weird when you venture away from the world of functions and control flow. So we have a very similar example here, but this if is now executed inside an async.execute. And what an async.execute does is it takes the body of the operation and it puts it on some runtime, and it gets executed in another thread, for example. And then it returns a token, and we can await on the token and say, wait for this region to stop executing. So we have the same situation. The store of %arg0 is the nearest dominating store of var to this load, and say, OK, well, we can just promote this thing off the stack, right, and directly use %0. This is fine in this situation because async await guarantees that the region executes before the next store. But if that's not there, then this transformation becomes invalid because the store of arg0 could execute before the region does, and so you have a race condition. Or the function could return, and the variable is now no longer on the stack, and you get a use after free. Another example is scf.parallel. So one thing about scf.parallel is it does say that the regions can complete execution before the end of the operation. OK, well, we have this %tensor and %tensor0, which are defined to be the same value, a width constant of 0 for by 32. OK, so let's CSC them, right? The problem is that SCF parallel can lower to async executes. So you spawn a bunch of threads that run the body on the iteration space and then wait for them all to complete. Or it could lower to GPU launch, which means that you actually offload the computation of the body to another device. But now the question is, where does the memory for this tensor live? Because a tensor will lower to some memory allocation that gets put into a memref, but we've just replaced the tensor allocated in the body, like could run on a GPU, with a reference to memory allocated on the CPU. So essentially what you end up happening is CSE creates a load of the host memory on a device, and then this will crash.
So, I mean, yeah, fundamentally the problem is that dominance it's sort of a dynamic property that's converted into like the static thing. And MLIR just believes that it really is a textual property of the IR in terms of nesting. And so, yeah, we need to somehow like find a way to communicate what the operation really means instead of like always assuming that the dominator trees should be connected. So Jeff, how do we implement this, and what are the problems with this?
Yeah, so the problems are like things like mem to reg are not going to work on regions in general in MLIR without this. Anything that uses dominance like LLVM does is not going to work in general with MLIR regions. This can be CSE, as we've seen, dead code elimination, loop invariant code motion. Even canonicalizer patterns that match across regions will break because they assume that there's some uniformity or some flow of control flow. It doesn't check where the SSA value comes from. It is, oh, I'm using this thing, but it turns out it's defined in another region. So what do? Well, in MLIR, you define an interface, right? You allow operations to specify their semantics in some way that can be used in general. One way we could do this is that an operation defines how the dominance of its parent region connects to the child. So an op can say, please disconnect the dominance tree from the parent region to my regions. You could also perhaps describe the relationship of liveness. So what is the liveness of implicit captures across my regions? And you can even ask the op, do you change the semantics of operations in your region? So let's see how this can work. The way we should remedy this async execute example is mem to reg is running and goes, I don't understand this region. It's not control flow. But there is a use of %var inside this region. And because the mem to reg could just go, I give up. I can't reason about this and not promote this, which is correct because promoting it in this situation can be incorrect. SCF parallel is a little stranger because what it is essentially doing is operations inside the SCF parallel could be GPU ops, but operations outside the SCF parallel could be CPU ops. So SCF parallel changes the semantics of the operations in the region. For those who are familiar with the quant dialect, it does something similar and was also very strange. So perhaps this operation should just be isolated from above. But if you need finer grained reasoning, perhaps we should allow SCF parallel to say, hey, be careful with hoisting or anything in CSE because moving an op outside of my region could change the semantics. And because MLIR says operations define the semantics of its regions, that can be possible. So one last thing is this is not a final design idea, but I think that it is really important to get this working in MLIR. For example, in Mojo, I added a trait that says, is a control flow region. And so our implementations of mem to reg and all of these optimizations can work when you have inline closures, inline async regions, and so on. But we can't really upstream these. We'd love to, because MLIR in general does not have this as a core semantic, and dominance will break if you try to run mem to reg on some general MLIR ops. So we'd love to hear your opinions about this, as well as your questions. So
Thanks.
That's it.
Do we have any questions? Good.
All right. Well, thanks for exploring this. I'm very confused by some of your claims in this talk.
Oh, really?
Yeah. First, the syntactic versus semantic, which I don't think is a correct analysis of MLIR language reference.
Okay.
If we talk in terms of pure dominance, right, it means that an operation is a value. An operation that produces an SSA value must be executed before the users, right? And I believe that this is a semantic property that is enforced by region. Mm-hmm. I would want to see an example of a region where the control is transferred inside the region without first going through any definition of an SSA value, which would be breaking dominance, right?
Yeah, so I agree. I think it's more subtle than that. So I feel like, maybe we should take this offline, but it's like in some sense in LLVM, when we have dominance, we know that it's going to be intra-procedural. And so we have this notion that dominance and liveness are the same thing. So we have this guarantee that when control flow moves from one basic block to another, variables that used to be live continue to be live, while it's like in MLIR, this is no longer the case. So it's not syntactic exactly, but it's something like, yeah.
More or less,
yeah.
In terms of liveness, we could make example also in LLVM where if you malloc a variable, you get an SSA value. The liveness of the memory allocation is totally decoupled from the dominance or the availability of this value. You can have a path that will free this SSA value, and you can use it after free, right? So you get, again, in LLVM, something that is decoupled between liveness and dominance.
That's fair, yeah.
And so I think there's more subtlety in this than anything.
Okay, yeah.
And one more things where, I'll disagree with Jeff on this. I don't agree with your for a parallel for example, where like this is to me not semantic changing. First, because SCF parallel doesn't know anything about GPU, and like materializing different memory space becomes a lowering problem.
But do lowerings define the semantics of the ops?
Absolutely. If a lowering supports SCF parallel on GPU and SCF parallel supports implicit capture of tensor, like copying the memory and making it available is part of the lowering.
So you would say that it's actually a bug in the lowering, not in the...
If the lowering doesn't support that, yes, it's a bug in the lowering, clearly. And if your lowering requires to have an isolated SCF parallel, you cannot use SCF parallel, you have to use another op. But at this level of, like, if you take the semantic description of the IR here and this transformation, it seems to me perfectly valid. If your lowering doesn't support that, that's like, you're outside of the semantic of the IR. It's not this transformation that is broken.
I see. I guess I'm more indexing on the lowering being the source of truth, the semantics of an op, more than the, ODS documentation of the op itself.
Yeah, we would have to look at the lowering. I don't know what the
lower
GPU mapping
launches.
of this does. Anyway, thanks for. I think you were onto something with the async things where we need interface and we need to think about how to model this deferred execution.
Because a lot of these passes do need to reason about like dominance in the LLVM way, but then the way it works with regions in MLIR isn't always like that, and so these passes are struggle to get them to be correct.
Yeah, so maybe one thing that I wanted to note is like, I feel like we should maybe take a real hard look at the taper stuff where they designed fork join parallelism in LLVM. So they had a nice way to extend the dominator tree information with like a very mild amount of info such that most of the passes didn't need to change, but the optimization still worked. So maybe that's like a good reference to like actually think about the design if we want this to be robust, because they've thought through many of these issues. Yeah.
You mentioned you're looking at a new interface maybe, so I'm wondering if you can do something with a region branch op interface maybe. Like for the async op saying that you actually don't branch into that region at all from the parent.
So it does implement region branch op interface, async execute does. And then there's a question as to what this interface actually means in terms of control flow and liveness. The concept I've used is like contiguous control flow, meaning that as soon as this op runs, it will move the program counter into its body, and therefore you get the same kind of effect as dominance in the LLVM. But then you can also describe like higher level ideas about control flow. Yes, an execute does move control flow into its region, but it's not like updating a program counter, for example. Same thing with SCF parallel. You can describe it as being a loop, but actually there's some more interesting things going on there.
Yeah, I was wondering for the async op in particular, does it actually? It won't execute immediately, right? So does it actually? It should.
It could execute immediately. It could execute later. It could execute once you hit the await. It depends on the implementation of the runtime. But it basically means go start running this region somewhere. And the guarantee is that once the await finishes on the token, then that execution completes. It could run immediately. It could run later.
So maybe we could add something like maybe it goes inside, maybe it doesn't. Just.
Yeah.
So this very thing bit circuit just 2 weeks ago, where someone started using regions for something completely new and interesting, and we had to go take all our canonicalizers and restrict them to a single region, because What they were representing with regions were concurrently executing pipeline stages in a hardware design. There's no such thing as control flow or op executing after next op. So maybe even slightly more general consideration on how we describe dominance, because in many other places in the pipeline, we do also try to use the notion of dominance, though there's been some algorithmic complexity problems, which we can talk about offline.
Were these graph regions or SSA CFG regions?
I believe they were SSA CFG regions, and for reasons also had multiple basic blocks. I wasn't involved in this, I just had to deal with the fallout.
Okay, interesting.
Yeah, I'm sorry, I think we're out of time. So we'll set up the next talk. Let's thank our speakers.
Thank you.